for this. I hope it's not going to occur like on a regular basis. So let's hope it's only a glitch for today. Okay, so I'll start with questions from the homework. So anyone has any questions? So raise your hand here, and we'll take up some of the question you may have regarding the homework. Any questions? No? You're all good. Okay, a couple of things here, like starting like tomorrow, I will ask you to enable the video. I need to see you. Now, I know that everyone else will see you, but I need to see you. I make sure that it's you and that you're doing like you're in front of the screen, like making notes and all this. So make sure that you're dressed properly. All right. So I don't want pajama or whatever it is. Okay. And so we'll start tomorrow for that. Okay. All right. So if there's not any, yes, no, you don't. No, Leo, you don't have to to dress in uniform, as long as it's decent. Okay. All right. That's all. No, you don't need. You don't need to. Okay. So if there's no, oh yes, David. No, la 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 la. You don't have a webcam. That's bad. Anyway, we'll find out something. We'll find out about this. Okay. Okay. Any other questions? No. Okay.
Wait, Mr. Leduc,
Yeah.
it's okay if my webcam's like 70p?
I don't care. All right. I'm not looking for quality. Just want to see if it's you. And sometime I'm going to ask you, okay, you can turn it off. Like, that's fine. Okay. So it's not all the time. Okay. Not all the time. Okay. Any other questions? All right. So homework was okay? Yes? Do you do your homework? You have to do your homework, guys. Okay. All right. So if there's no other questions, so let's start. So let me share. What is this? A plugin is required to share an iPhone. What is this? That's new? Okay. All right, guys. So just you have to wait a little bit here. I don't know why. Okay, there we go. That's kind of new. Probably it's an update. All right, so you should all see this here. Okay, so let's continue what we so as usual here. If you need to ask a question, I don't look at my screen all the time, so just give me a shout. Okay, so the review here is we learned yesterday about the network, right? So the network is the work done by all the forces on a body here. All right. What else did we learn? We learned about kinetic energy, which is the energy of an object as a result of its speed. And then we learned the work energy theorem. This is the very first clue that work and energy are somehow related. Okay. So what we learned here, we learned that the net work done on an object is equal to the change in kinetic energy of the object. All right. Okay. So once again, it's called a theorem here because you could derive this mathematically, at least for point particles. But this is a more general formula. This is a more general principle, right? Although this can be derived like mathematically from Newton's second law, actually, this is much more than Newton's second law. Okay. All right. So let's. So what we'll do today is I'm going to show you we're going to take a more difficult like example. We're going to apply like work energy theorem, but we're going to use a more difficult example. So let's start with this here. So example. So a 3 kilogram mass has the following forces acting on it. All right. So what we're going to have here is we're going to have a horizontal section here. And then a slope. And we're going to make this slope at 30 degrees. And then, so this is our block right here. And we're going to assume here that along the horizontal, it has this much displacement here. So along the horizontal plane, I'm going to call this delta DH. So let's say here, this is like, let's say 5 meters. And the forces acting on it will be as follows. So there'll be an applied force, okay, at an angle of, let's say, 60 degrees. We're going to have, of course, gravity, the weight. We're going to have the normal force. And yeah, so this is going to be like frictionless for now. And then when it gets over here, so let me put it here. So when it gets over here, okay, hold on a second. Let me erase this. Whoops. This is the block right here. All right, so it will go up like the slope, the inclined slope, a distance of, let's say, 3 meters. Well, let's say 4 meters. So on the slope, we're going to say here the displacement is 4 meters. We're going to have like some friction. I'll give the value in a second. FA will be exactly the same as it was before. So FA is exactly the same as it was before. We're going to have, of course, gravity. So the weight going down. And then finally, we have the normal force. It will be like this way. Okay. So this is the diagram here. And the value here, I'm going to give you the value. So the value for FA will be, oh, let's give like 17 Newton. Friction here will make it 5 Newton. All right. So the question will be as follows. If the block starts from rest, right, finds its speed, find its final speed at top of incline. All right. So what do we want here is we want to find the final speed here. Of course, it starts from rest, so the initial speed will be 0 meter per second. All right. Okay, so let me see here if there's more people. Navid Nethu, don't know this guy. Yeah. All right. So this is what we have right there. Now, if you could sort of do this problem using Newton's second law of motion, it would be like a little bit like long, but you can do this. My purpose here is to sort of use an energy method to do this problem. Using energy, it's always easier because you don't have to care about direction, don't have to care about the X and Y direction, right? Because work and energy are scalar quantities. What's a bit like different from what we've done yesterday is that the block doesn't go along a single direction. So it changes direction here. So in order to sort of find the final speed here, what we're going to do is we're going to use the work energy theorem, right? So we're going to sort of try to find a network, and we know what the kinetic energy is, the initial kinetic energy. In this case, it's 0. So if we found like the net work, we'll be able to solve for the final kinetic energy. And since we have the mass, we'll be able to find the final speed. So we're going to use like work energy theorem to solve this. Now, as I said earlier, so let me sort of put it this way here. All right, so let me see here, some MATLAB. There you go. Is Max here? I don't know, I don't see Max. Is Max around? Does anyone know? I don't see Max. Does anyone know if Max can join us? Anyone?
I already tried messaging him, but it doesn't seem like he's checking his phone.
Okay, all right. Okay, thanks. All right, okay, so what we're gonna do here is this. We're gonna sort of split it into two parts. So the network, so network, we'll split it into two parts. We'll find a network done along the horizontal plane, which I will call like WH, and the work done along the incline or the slope, which I will call WS. All right, so WH is network done along horizontal plane. And WS, network done along the slope. All right, so we're going to split it into two here. So let's start with the work done along the horizontal plane. Well, along the horizontal plane, what do we have? We have 4 forces. Therefore, there will be 4 terms. So there'll be the work done by normal force, the work done by gravity, and the work done by the applied force, right? Now, right away here, there's a couple of terms we don't have to do any calculation, and which one are these? So hands up. Yes, well, Madav, you're already there. Okay, yes,
The WN and WG are
that's correct.
perpendicular. They're
Because
perpendicular to the
that's correct.
movement.
That's correct. Perpendicular to the displacement. So this is 0 because Fn is perpendicular to delta D H, and the same thing as this one here, because Fg is perpendicular to delta as the slope. Very good. Sorry, H. Excellent. Now remember what I told you here yesterday. In order to sort of solve those problems here, you do an FBD, but you put the displacement vector on top of it. So let's do like for the very, very first part. So what do we have the very first part? We have the normal force. We have Fg, the weight, and we have Fa. And of course, here we're going to put the displacement, right? And this angle here is, of course, like 60 degrees. So that's going to be like delta A, right, is 60 degrees, right? So what we're going to have here is, so the net work along the horizontal is nothing else but the work done by the applied force. And once again, the formula is the force times the displacement, all of absolute value, times cos of theta A, where theta is always the angle between the displacement and the force. All right, so there, what did I give you? I give like 70 Newton. So it was like 70 Newton times 5 meter times cos of 60 degrees. I don't know. What's cos of 60 degrees, guys? Is it a half or root square of 3 over 2?
0.5.
Okay, thanks. So it'll be, so 350 joule times 1/2. So remember, Newton meter is a joule, and I'll give us this. All right. So this is the work along the horizontal. All right. So this is a network. Now you notice here that the network is positive. If the network is positive, what can we say about the block when it gets over here, just before the slope? So what can we say about the block? Is it Madav again? No. So what can we say? Yeah, David. That's correct. So you remember here, like when the net work was positive, it helps to speed up the object. The object has sped up. So exactly. So by the time you get there, before the slope, the object will have a greater speed. Now, you don't need to use Newton's, you don't need to use work energy theorem to find the speed there. You could, but you're making your life a lot more complicated than it is. What we're just looking for the speed right here. So let's compute like the overall net work along the horizontal plus the one along the slope, and then we'll be able to use like the work energy theorem to find the final speed. All right. So the second part is, of course, let's find the work along the slope. All right. So can anyone tell me what are the terms we're gonna get for the work along the slope? How many terms do we have? How many terms would we have for the nets? Yeah, David again. Yeah, just put them all for now. Yeah. Yeah, so what would it be? And force, this one thing. Very good. So we have 4 terms here. Excellent. So we have the work done by the normal force, the work done by gravity, plus the work done by the applied force, plus the work done by friction, right? So we have 2 terms, 4 terms. Is there any term that is equal to 0? Any terms? David again? Is it only David? Is there? Okay, Stephen. There we go, Stephen.
Is it the normal force?
Are you asking me? I'm asking you.
Well, if the normal force is perpendicular.
Okay, so this is 0, right? Whoops. This is going to be 0. Very good. We're going to do this. Now, is the gravity also 0? The work done by gravity, is it also 0, guys? Yeah, Stephen?
It's not 0 because it's not perpendicular.
That's correct. So in the previous case, if I go back here, you can see here that the force of gravity will not be perpendicular to the direction, to the displacement vector. So gravity is doing work. And as a matter of fact, gravity is doing negative work because it helps to slow down the object, right? As it goes up, of course, something will slow down, right? If there's nothing else. All right, so that's very good. So how do we get like our angles? So this is where you have to sort of go back to an FBD. So let's do an FBD here. And then what I would suggest you do is, because now it's going to be a little bit more complicated here, I would suggest you put a hatch line here, a vertical and a horizontal and vertical. All right, there's a reason why. Now we're going to put our forces. So let's put our forces here. So we have on the slope, we have gravity down. Now remember what I told you. I told you that the force, the applied force here is exactly the same. Okay, it's getting there. It's a little slow. The applied force here is exactly the same magnitude and also the same angle with respect to horizontal. It's exactly the same. So if it's exactly the same, then what we have is that we have that FA will be, now let me put it a little bit. So FA will still be at 60 degrees, right? Now, what is, in which direction would the friction be, this case here? Which direction would the friction be? Remember, bad friction is always opposite to direction. So which direction would the friction be?
The opposite direction as the force applied.
Okay, so in this case, so give me some degrees here.
Would it be 60 degrees off the axes?
60 degrees off the axis. So what do you mean here?
So like
You mean like opposite to the applied force right here? Oh,
Yeah.
that's what you're saying here? So you're saying here it would be, let me see here. Saying here it would be like this.
yeah, with the angle between the axes and the friction at 60.
Okay, but is the friction here opposite to the applied force? Is that what you're saying?
Uh,
Yes,
Okay.
no?
yeah.
Okay, no. Well, it's a good try. Okay, yes, Stephen. Stephen?
Would it be like south 30 degrees west?
Yeah, it would be, this is exactly, whoa! Ugh. Yeah, but like the, I have to redo this here. All right, so that was this. Let me see here. Okay, so that was the force here. Force of friction. Yeah, you can see this force of friction here is along the plane. It's always along the plane. You remember, any contact force can decompose into two components. A component that is 90 degrees perpendicular surface of contact and that we call normal force, and the component that is parallel surface of contact, which is in this case friction. So friction is 30 degree down here, right? Whoops, where's that? It's exactly this, 30 degrees. So I'm gonna come back here. Let me put it here. So it is friction 30 degrees here. So that's why I ask you to put little hatch line here, the vertical and the horizontal. And Fn, well, Fn will be 90 degrees perpendicular to the friction. All right, so, but we don't care about normal force because it's always perpendicular here. So, so it's going to be something like that. Okay, so that's the normal force here. And now what we're going to do is we're going to put the direction, the displacement. And displacement is 30 degrees with the horizontal. All right, so it is 30 degrees with the horizontal in this fashion. So we're going to put it right there. So let's go back. So it's going to be this.
Sir,
Yeah.
shouldn't the angle for the friction there be 60 degrees?
It's 30 degrees, right?
Yeah, it's 30 degrees from the bottom, so it'd be 60 from the top.
It's like this here. All right? No, it's 30 degrees.
It's like a Z pattern.
Yeah, it's the opposite. This angle is the same as this angle, right? Right? So, so it's going to be, so this will be exactly aligned with this. All right. So, and it will be like 30 degrees. So that's delta ds.
Oh, yeah.
Yeah. So once again, this friction here and this are along the same line. Okay, it doesn't look like the same line, but it's along the same line here. Okay, so now we're ready to figure out the angle, because if I go back to this, this is equal to what? This is equal to Fg times delta d s times cos of the angle between gravity and the displacement. All right. And then we have this. I don't have enough space here, but I don't have enough space to expand this, but I'll expand a little bit on the bottom here. Now, what is this angle here? What is the angle between gravity and the displacement? Well, it's going to be this here. So let me sort of put a color here. So this is the angle between gravity and the displacement. And what is it going to be equal to? Well, it's going to be equal to 30 degrees plus 90 degrees. So it will be 120 degrees. Everyone sees that? So once again, it's always the angle. It's always the angle between the displacement and the force. And you always choose the smaller angle, guys. Even though it doesn't really make difference with a cos, but always choose the smaller angle. Don't choose the bigger angle. Although you're not going to make any mistake mathematically, but don't use the bigger angle. Just use the lower angle. Okay. We need also to find the angle between. So let me continue here. Okay. So. All right, so let me continue right here. So WS is equal to FG times delta DS times cos of that. Now, the work done by the applied force is going to be this. The applied force times the displacement along the slope times cos of theta A, where theta A is the angle between the force and displacement. And finally, this one right here, it's going to be plus friction times delta ds times cos of theta f. All right. Now, what is the angle between the applied force and the displacement? It's going to be this here. So that's theta A right here. Put my A a little bit too big here. Doesn't look like a subscript anymore. So A. And what is A equal to? Yeah.
Eric wants to join the class.
Yeah. Okay. Thanks. Eric who?
No, it
Eric
should be
who?
Eric G.
Yeah. Tell him to put G next time. Okay. All right. So what is the angle here between the applied force and the displacement? Well, you can see here, this is 60, whoops. This is 60 degrees right here, and this is 30 degrees. So the angle is going to be 60 degrees minus 30 degrees. And it's going to be 30 degrees. All right. So that's the angle between the applied force and the displacement along the slope. And finally, we need to find this one. Well, it's pretty easy here. This one, it's always the angle, well, for bad friction, for distributive friction, it's always 180 degrees, right? So theta F, of course, is this angle here. So this is theta F. And of course, theta F here will be equal to 180 degrees, right? Because it's exactly opposite to the direction of the displacement. Okay, any question? Okay, so once again, so whenever you do something a little bit more complicated here, please get to a habit of doing an FBD. Put in a hatch line a vertical and a horizontal line so that you sort of put your vectors at the proper orientation, and then you can sort of do your calculation here to find what the angle will be. Okay. All right. So if I continue here, please resist the temptation to factor out delta ds. Okay, I know you could do that, and then what you would get, you would get like the component of each force, the net component of the force along the slope, but I don't want you to do that. Okay, so just leave it there. Okay, don't do that here. Okay. So we know that this is equal to mg times delta ds times cos of 120 degrees plus fa times delta ds times cos of 30 degrees. And then here it'll be like plus f times delta ds times cos of 180. So let's plug the values in. I don't remember what my mass was. Was it 3 kilogram, guys? 3 kilogram?
It's 3 kilograms.
Okay, so 3 kilogram times 10 meter per second square times, what was my displacement along the slope? 3 meter? Was it 3 meter?
It was 5.
4.
Oh, it was 4? Okay.
Yeah,
Oh,
4.
never mind.
4. 9. Now, cos of 120. So what is it? Is it minus 1/2 or minus root square of 3/2?
-1/2.
Negative half?
Yeah.
Okay. All right, so negative half. All right. Okay, good. Plus FA. So FA was, I don't remember, 70, yes, 70 Newton times 4 meter. All right, so here we're doing this part here. So cos of 30 degrees, I guess, is root square of 3/2, I would presume. And then finally, the friction. How much friction did I put in there? 5 Newton. Yeah, 5 Newton. So it's going to be 5 Newton times 4 meter times -1, right? So the work done by dissipative friction is always negative. It helps to slow down an object. All right, so let's put this here. Can I do this in my head here? So you can see here that the work done by gravity will be negative. It'll be like 2 times, so it'll be 60 joules. Am I correct, guys? Am I good?
Yeah.
Yeah. Okay, so it's negative. So due to gravity alone, since the work done by gravity is negative, it helps to slow down, right? Gravity, of course, helps to slow down an object going up a ramp. Now this one here, so be, what is that, 2? So 140 times, so it'll be positive. Can anyone tell me what is, well, we'll put it. So 140 times 3 joule. All right. And then finally, the friction here will be negative, and it will be negative minus joule. All right. So someone will put this in your calculator here. Well, I know that this one and this one will give me like minus 80. So minus 80 plus 140 times, so what do we get? Anyone? Yeah. Okay, do I have a confirmation here?
Yes.
Raise hand.
Rounds up though. It's 49.
Well, just give me, it doesn't matter. 1 decimal is fine. Okay, so 160 what?
162.5.
0.5. Thank you, Joule. All right. Thank you, Forrest. Okay, so so you notice here that the net work done along the slope is positive. So from the bottom of the slope up to the top of the slope, the object has sped up, right? It has sped up. Questions? Okay. All right, so third step is to find the net work. So the net work is going to be the work done along the horizontal, the net work done along the horizontal plus the net work done along the slope. I don't remember what it was. What was it? 175. Okay, so it'll be like 175 joule plus 162.5 joule. And that's too much for me to calculate in my head. No, I guess I could, but okay. I know there's a 0.5. It'll be 7. 3. Is that correct? Is that good?
Yeah.
Okay, good. So this is the net force. Sorry, the net work from the beginning up to the top of the slope. It's positive, so we know that by the time like this object is at the top of the slope, it will have a speed greater than it was at the bottom because the net work is positive. Okay, so fourth is we're going to use work energy theorem. So work energy theorem relates the net work done to the kinetic energy. Of course, here the initial kinetic energy is 0 because it starts from rest. And what do we find? We find that the net work is equal to the final kinetic energy. So it's equal to this. Right? So the final kinetic energy of this object at the top is 337.5 joule. This only because it starts from rest. If it didn't start from rest, well, it would be like something different. By the way, here you can sort of check if you made a calculation error because kinetic energy, by virtue of its formula, it's always positive. So if you get like a negative value for kinetic energy, double check, go back. You probably have made a mistake somewhere. All right, so the last step, we're looking for VF. Well, we know that that KF, once again, is equal to this. We know that this is equal to m VF squared over 2. And it's just a question of isolating for VF. So VF here will be equal to 2 times 375 joule over the mass. Let me see here. So 66, what was that? 66 plus, what is that? 14, 15. Is it like 675? I think.
Yep.
If I'm not correct, just let me know, guys. The mass, I don't remember the mass. What did I give for the mass? Oh, it's a 3 kilogram. Oh, I hope it, I don't know if it does divide evenly. I'm curious. Anyway, okay, so can anyone confirm that 2 times 337.5 is this? Is that correct? Yes, Forrest? Okay.
Yep.
All right, so so if you take the square root of all this, what do you get?
15.
15.
15?
Yeah, it's 225 inside the square root.
Really? Look at that. Another. That just, yeah, I'm amazed myself. Okay, so 15. Wow. It's like numbers I just chose out of my head. Very good. Okay, so is there someone else who wants to join in here? What's that here? Okay, chat. Is there a chat there? So
It's
this
actually
is
not
Funny
chat.
how he said, how about we
Oh,
round
okay.
to one
Look at his
decimal?
numbers. It's so
Smurfing.
perfect.
Yeah.
I don't know what smurfing means here. Are you referring to the Smurf, Stephen? What does smurfing means? Stephen, it means you're good. But does it have to do with the Smurf? It means it's too easy for you to get whole number. No, not the blue guys. Okay, never heard of that. You know how to say Smurf in French, guys? Anyone? No, it's not the Smurf. No, I've never. When I was young, like, of course, it was invented by a Belgian. No, it's not a Piston Bleu. No, it's called Schtroumpf. Yeah, Schtroumpf. There you go. I think that's how it's spelled. No, yeah, you're right. I think I forgot a M somewhere. I forgot an M between
You're
like
using
the
that during
U
this
and
French
the
oral.
P.
Yo, before you search that, just be like,
Smurfing means that you're very smart, so you pretend to be less smart to hide your. Oh, no, I don't do that. No, it's just a fluke. 2 in a row. Okay, all right. So are you good with this here? So once again, this is a little bit more complicated than before. Once again, you can use Newton's laws of motion to solve for this problem. It will be like probably a bit more difficult than it is right now. Why doesn't it like? I don't see. I don't know why it doesn't seem to move. Is it frozen, guys? The
No, I can see it.
no, but do you go because I went back to the first slide. Can you see it?
No.
No, we don't see the first slide.
All right. Okay. So yeah, I have like such a small. I have a very old computer. I can hear the fan go like crazy. All right, so let me share this again. There we go. So now we're back. So once again, you can do this problem using Newton's second law, but that would be like really, really difficult. It's much easier to use like the work energy theorem. And then later on, if instead, don't write this down here, but if instead of having like something with straight lines, if I had given you like a curve like this, right? Now you would probably be scratching your head if you want to use like Newton's second law, all right? But you're gonna find like very soon next week that you can do this problem like very easily by using work and energy concepts. You're gonna sort of find this next week. All right, well, that's it. So any questions?
Sir, did we ever decide about the afternoon classes?
No, I did. Did I send you a Google Classroom? Sorry, a Google form about this? No. So I will. Okay, and then you'll vote, and that's it.
Okay, thank you.
Any other questions? All right. So at the moment, if you check your website, you're going to see a handout, right? So please like print it and then do the problems. The problems are on work energy theorem. They're way like easier than the one that I've just shown you today. Okay. The one I've shown you today, I'm going to sort of give you like more tomorrow. Okay. So we're a bit like ahead of the problems per se. Okay. So tomorrow, like what you will have as homework is based on what you've learned today. Okay. So that's how it's going to be. Okay. All right. So if you don't have any other questions, well, yeah. Is there any question here? More. Chat. Okay, let me go chat. No, it will not be shared. So Rolf, you just I can sort of leave it there, right, for a little while, and you can copy. When a question refers to work done, oh yeah. So Josu here, like when the question refers to work done, this is what I asked you at the beginning of the lecture here, like, do you have any questions? Because sometimes it's unclear in the textbook if they mean the network or if they mean the work done by an applied force. So whenever I do like a problem, I set problems, you'll know for sure what I'm talking about. Are we talking about the net force, or are we talking about the work done by a force? Okay, so I will always be clear. Yes, Eric, I will sort of go back to the lesson for those. Okay. So if there's not any other questions, well, I'm going to ask you to disconnect for those who have no other questions here, and then you go by your day. And for those who wish to copy a little bit more here, I will be on for 5 minutes or so, and